So what are we talking about? We're talking about the highest possible frame rates. We're talking about smooth graphics. But we're talking also about minimal effort. You need to look at the Android APIs that are available to you and decide for your application which one's going to be the most appropriate to get a high-performance application. So that's the kind of thing we're going to talk about today, looking through and deciding which one of the APIs are going to make our applications responsive. At the same time, mean that we don't have to do more development effort than we need. So we have a canvas in Android. And with the canvas, we have Opengl, we have Renderscript, and we have the NDK. And these things all come together in the applications written on Android, in your applications, to provide nice, smooth interfaces. So if we have a look at the NDK and Opengl ES, this combination, along with the native window, allow you to access all the CPU and GPU functionality, the Neon and the Vortex, at the same time as natively accessing the Opengl. And it's this particular combination that will give you the highest frame rates in Android. An example of an application that uses these that you saw a second ago was Google Earth. And Google Earth is a native window meaning that you can push, you can access the GPU memory directly using Opengl. Get some really nice 3D rendering going. So Opengl has been around for quite a while. Many of you probably know about it. It's the closest to the hardware. Opengl was written for that in mind, across many platforms, to have one layer which lets you access the GPU directly, either through the Dalvik layer, through Renderscript, through NDK, many different ways of accessing the same thing. All of them give you access directly to the 3D hardware. If you have a look at the Opengl through the canvas, it's going to be the easiest way to do Opengl on Android, the easiest way to do 3D on Android. But you've got to bear in mind that you're in a canvas, you're in a surface view on Android. And what does that mean? The Opengl is happening on the native layer, and your surface view is happening on the Dalvik layer. So every single one of those Opengl commands you make is going through the JNI. It's going down to that hardware layer, and it's done on a per-command basis. There's lots of messages being passed up between the native layer and the Dalvik layer on Android when you're using Canvas and Opengl. But if you've written your entire application on the Dalvik layer, and you have some things you want to do in 3D, then this is a really good option. It's minimal effort for you, and you get a good performance gain. One of the applications that uses this particular method is Google Body. So this is all done up in the Dalvik layer using Opengl. And you can tell it's still very high performance. You get the textures, you get the layering. Of course, I know a lot of you out there are a bit more hardcore than that. You're not writing everything in Java. You guys, you miss your pointers. You want that direct memory access. You're thinking in the matrix. And if you miss having pointers, and you want some fancy graphics, but you don't want to do everything in the NDK yourself. You don't want to write all the NDK glue. You just want a small part of your application to be really high performance. That's where Renderscript comes in. And Renderscript is now fully supported in Ice Cream Sandwich, so new devices coming to the market have Renderscript capabilities. And if you look at the Google Books app, things like this on the Galaxy Nexus, you get the nice page-turning animations that you saw on Honeycomb before. And the Renderscript APIs are now much better documented as well. So I'm hoping to see many, many more hero screens, things like this, inside your applications as they come into the market, now being able to use Renderscript. And I'm going to give you some code examples and demos of Renderscript in a minute and show you how easy it is to access this layer from your Dalvik code without having to write too much glue. It's the beauty of Renderscript. It just sits as a .rs file, a script file, inside your application at the code level, and it gets transferred to the device as a script file. And then there's a compiler on the device that takes that script and compiles it into native code on the device. So the device compiler just needs to know about the features on that device to give you a way of making native applications that work across the entire range of devices. If you were using the NDK, you would compile it yourselves and then push it out, and it would work on that set of devices. With Renderscript, the compilation happens on the device. Again, the YouTube wall of videos is done in Renderscript, and it was done on Honeycomb, and now these features are available to you. It's C99 programming language. You have your direct access to pointers. You're supporting the resources, and a much, much easier glue to the Dalvik code and that compilation than using the NDK. It's a little bit easier to debug as well. Still challenging. Has anyone started using Renderscript at all? Has anyone looked at the Renderscript, made some little scripts? I've got one. There's one. There's one. There we go. Two. OK. So now Renderscript is in Ice Cream Sandwich. It's in this new SDK. It's better documented. I highly recommend looking at it. And I'll show you some examples later on of how you can utilize it for much higher frame rates on Android. Switch to the OpenGL SDK slide at some point. So the point of that was, compared to Renderscript, you get the flexible porting of code across platforms. If you've written your game for other platforms, if you're writing it for Xbox and iPhone and Android and all these at the same time, then you can port your game engine more easily if you're using the NDK. And that's really why the NDK is so important to Android, to get all these fantastic high-performance graphics engines and games working across all the platforms with minimal effort. And then you write your glue, and you do your Dalvik layer, your menu systems, things like that. And it's that's definitely more challenging to debug. Some of the chipset manufacturers have released tools, NVIDIA, for making debugging the application that's running on the GPU a little bit easier, but it's still kind of tricky. And then that native window that I mentioned earlier as being the way of getting that direct access to the frame buffers. So Android, from the start, the canvas in Android has been core to graphics on Android. I mean, all Android developers in the room will know about the canvas. There's lots of examples about the canvas. You probably used the canvas, especially if you're creating your own widgets or views, things like that. It's the one thing that has the most direct operations on it for doing rotations and blending and spinning, all these kind of translation across the screen, all very easy, kind of one line of code, animations, things like that. And it's used a lot in the Android UI as well, in the Android framework. You can skew, you can bounce. And if you're looking at optimizing that canvas, optimizing the simplest way of doing graphics on Android, then there's a couple of things. One is to draw the smallest number of pixels. Don't wipe out the entire screen every time and redraw all your elements. Have a look at the clip rectangles. Just redraw the things that are changing on the screen at any one time. And if possible, much trickier actually, is to draw each pixel only once. I mean, it may involve writing a bit more code or quite a lot more code. But as you can imagine, controlling which pixels are changing can really help the memory throughputs of the device, things like that. So general guidelines for making graphics faster on Android. Invalidate the changed regions only. It's kind of common sense. Set the background thread priority to background, which is an interesting one, because we always say the main thread of your Android application is the UI thread, and you should only do UI on the UI thread. Don't do any processing, disk write, SQL, HTTP, web access. Always put those things on a separate thread. But when you put them onto that separate thread, it's also worth bearing in mind if you want your UI to be the highest performance, tell the system that that separate thread is a background thread. So the UI not only gets to keep running at its top speed, the system will give it even more resources. We have some tools in the Android SDK. Using shallow view hierarchies, you can use the hierarchy viewer and layout optimizer to check your view hierarchies. Again, there's been blog posts about this kind of thing. And it's another one of these examples where you might have to write a few more lines of code. But if your application's not running as fast as you want it, you can switch from embedded linear layouts inside linear layouts inside linear layouts, switch that to one single relative layout on a single flat view hierarchy, and you'll get a much faster measure and draw cycle. And the layout optimizer tells you about that. The hierarchy viewer points out things in your code which are taking a bit longer. So all these things, as I say, they're not absolutely necessary, but if you want your code to run faster or you notice a glitch, they're things that you can do in your code just to make it that much better and that much buttery smoother and that much more likely to get featured, because in the back of everyone's mind, they have that thing where if there's a slow frame rate or if your application's not as responsive as they think it should be, they're going to think it's lower quality. And as soon as you manage to speed it up, if your application's faster than someone else's, if it's smooth, you get that impression, that feeling of high quality inside the application. And then we do as well, whilst we're testing it. So the canvas. We're going to talk in detail about a couple of new acceleration methods in a minute. One of them is the layers, and the other one is display lists. I think this slide is a little premature when it says consider using layers when hardware accelerated. But maybe you already know what layers are. Who in the audience already knows what a hardware layer or a layer in Android is? There's a few of you. Cheers, Nick. That's great. So we're going to run through what layers are and how you can use them in your application to make things super smooth. And scaling images yourself, again, it's slightly common sense, but don't just give an enormous image to the Android framework to scale down onto the screen. Scale it yourself, pass it the small version of the image, save some memory, save bandwidth, render faster, especially if you're going to be animating it. That's just the example here of just instead of passing the big bitmap into the Android framework, just that small amount of extra code to scale it down on the way through, it's just going to have an effect on the amount of heap size you're using at the time. Okay, so enough direct talking. Let's have a look at some examples, some code, some high-performance graphics on Android. We're going to have a look at a canvas, we're going to have a look at some Opengl, and we're going to have a look at some Renderscript. So first of all, we'll switch to the tablet, hopefully. Hey, that was Google Earth, just so you didn't see my screen before. But Google Earth was native window, NDK, OpenGLES, that high-performance package. So here, a simple canvas application written in Android. We've got some fragments, but the main one on the left is a surface view. It's an Android surface view. It's kind of based on that lunar lander example, and it works. Inside the surface view, we have a separate thread running, and all that thread is doing is updating the kind of the physics model of the view and then drawing it. Just update, draw, update, draw, update, draw as fast as it can. And it's managing generally like 50 or 60 frames a second on something very simple like this. The benefit of this is it takes kind of 10 or 15 minutes to knock up. All this is doing, I just grabbed an image off the internet, and then I'm drawing the canvas. We'll see the code in a sec. I rotate the canvas, draw the hand, rotate the canvas again, draw the second hand, put it onto the screen, minimal code, and it kind of looks okay. Oh, I'm using the clicker instead of the tablet. So the second one is going to be a very, very basic OpenGL, just texturing a triangle and spinning it around on the screen. This is OpenGL from the Java, from the Dalvik layer of Android. You can see how we're going to create this surface view, texture a triangle, and spin it round. And the third example is going to be the Renderscript one. So this here, big black window, is a Renderscript window. We've assigned the entire view space to Renderscript. And at the moment, when I touch it, the Dalvik layer is going to receive those touches, and it's going to pass them through the Renderscript glue onto the Renderscript layer, and the Renderscript layer is going to start a small fountain from every place that I touch. So I can put a finger on the screen, and hopefully you can see things starting to appear. And if I put all 10 fingers on the screen, you get 10 little fountains running down. All those particles, which are hundreds of thousands of particles on screen at the same time, are all done on the native layer in Renderscript. And I'll show you now, when we switch back to the laptop, how those three demos are implemented on Android. OK, so the stopwatch is a surface view. And the surface view is there to give you access to the canvas on the Dalvik layer. If I scroll down, you'll see there's some variables at the top, just me mucking about. But importantly, it starts here, public stopwatch. And we initialize, and then 3 methods that do anything. We have the run method, and it just sits in a loop, running as fast as it can. I put a little 30-millisecond sleep at the end, just so the UI stays interactive. And the run loop is spinning, spinning, spinning. It locks the canvas, does the draw, updates the physics, sorry, then does the draw, and then unlocks it again. And this mechanism of locking and unlocking the canvas is double buffering for us automatically, which is really handy. If you just grab a canvas and start drawing to it, you may find you want to draw off screen and put it on screen and do these things yourself. But if you lock the canvas and then unlock it again, you get that double buffering, speeding up your graphics built in for you. So we only have these 2 methods that are executed, update physics and do draw. And this is to draw that spinning stopwatch that we saw a minute ago. Update physics just figures out the angles for the 2 hands based on the current milliseconds. And then do draw is this one, which draws the background, draws the clock bitmap and the thing at the bottom, and then does the rotate to draw the hands. So you can see that this little element on the left-hand side before, the stopwatch element, is actually really simple. Oh, there's the lap times. I've gone too far. Where's my hands gone? Hello? OK, it's these ones. On a canvas, you don't rotate the graphic before you put it on the canvas. You rotate the whole canvas, put the graphic on, and then rotate it back again. So it's these 2 little chunks of code where I'm doing the rotation of the canvas, setting the bounds so I know where to put the hands, and rotating it back again. This is all open source anyway, if you search for Ultimate Stopwatch. And it's based on the lunar lander example. So a canvas, you can do this very fast update loop very easily, and you just put the surface view onto the screen, set content view, set display to this, and you're going to get quite simple animation. But as soon as it gets complicated, it's going to slow down quite quickly. You're going to want to use other methods. So if I can get my mouse back, we just we'll next have a look at the surface view. So this was the OpenGL example with the spinning triangle in the middle. So you start with your activity, as you always do. You've got your onCreate, and this is the entire activity class. The onCreate, onPause, and onResume. But the onCreate, all it does is creating a new GL surface view and setting that to the screen. And this GL surface view is up here. It's also very simple, because all the GL surface view wants to know is what you want to render to it. So you do, say, set me up, which is the first one, set EGL context to OpenGL version 2, and then set the renderer. And when you're doing OpenGL, you write your renderers, and you let them come to the screen. And the renderer is here. And the main part of this is the onDrawFrame method. The first one's just setting the vertices for the triangle that you saw. And the drawFrame in OpenGL, very similar to the canvas, that you're clearing the buffer first of all. So we clear the color to the background. And then we activate our textures. When you look at OpenGL, for people who haven't been doing OpenGL, you get these setup steps. And they look a little bit daunting. But there's a lot of really, really good OpenGL examples online. And you look through the examples, and you'll notice like the boilerplate at the top of many of the examples is kind of very similar with setting up textures, setting up triangles, loading models, things like that. And once you get through that, the actual drawing is pretty simple again. So there's a rotation multiplier, and then you draw the arrays. Again, this is an open source example. And it's all done in the Java layer again, but we're accessing OpenGL. And this is where I said before that if you access OpenGL this way, all of these commands that we're doing, GL20 or GL20 vertex attribute pointer, all these things are getting sent by the OpenGL surface through the NDK, or through the JNI, through the native interface, down onto the native layer. So there's lots of little messages getting sent up and down. And as you can imagine, it's going to be more higher performance if it was all written at the native layer, and we just send one message down and it all executes. But this is easier. This is more simple. You just send these messages down, and they get processed for you. and then you end up with a spinning triangle. Well, hopefully something slightly more complicated, because a spinning triangle is not going to sell very well. So the third one was the Renderscript, and I'm just going to jump back out quickly here so you can see the structure of the Renderscript project. It's this fountain one down here. Ooh. Okay, so as you can see, there's one extra file in this fountain project, the .rs file. As I say, you write your Renderscript. It's a C99 script, and you don't compile it. It just sits there in your package and is accessible. And it looks like this. Actually, let's go through the thing. So you get your activity, same as activities normally are. It's got a couple of methods. OnCreate, which sets the content view to the fountain view, and then an onResume and an onPause. Simple activity. What was that at the bottom? Oh, the log. Simple activity. Set your content view to the fountain view. In the fountain view, it's doing that processing of the touch events that I mentioned earlier, which is down here. So every time I touched the screen, you saw those small fountains appearing, and those touch events were captured in the Dalvik layer, and they were captured here on touch event on our fountain view. And it's the same touch events as you see, motion events in the other applications. Motion event.pointer up and pointer down. And what's new is these mRender calls. And these mRender calls are the glue to the Renderscript. And mRender, as it said at the top, is our glue class, which is fountain rs.java. So this is the class which sits in between our Java layer, our Dalvik layer, and our Renderscript layer. And when you're on here, first of all, you're going to bind to the script, but then you'll see these here, these script functions. This is the Renderscript and the resources. And then this method here is the touch position. So in the glue class, every time I touch, it sends a new touch position to the, in the view class, when I touch, it sends a new touch position to the glue class. And here, it does things like mscript.invoke add particles. This one here, and that's the glue itself. This is the script function inside the Renderscript, which is taking you from the Dalvik layer to the Renderscript, which is going to be compiled natively on the device and run on the GPU for you. And you can run calculations on the GPU as well as graphics. It's really powerful stuff. And then finally, the thing you actually want to see is the Renderscript itself. And that looks like this. So here's the C99 Renderscript uncompiled class, which is a script that's going to be shipped with your APK application onto all the devices that your application goes onto and compiled using a compiler on the device. Again, this is another open source example. It's called Fountain, and it's part of the Honeycomb SDK and the Ice Cream Sandwich SDK. And it does some setup at the top to set up the mesh, that entire view that we were talking about before. And then the add particles, where is it? Is the method that the onTouch was calling. So that is pretty much, this one here is the entire code pretty much for generating all those little particles and putting them on screen using the GPU directly. As you can imagine, this is much easier to do than doing the same thing in the NDK. Getting some random colors for the particles. But, and this is, while rate minus minus, this is while the particles are falling down the screen, changing their XY positions and their colors, sorting them out. Simple enough stuff. Okay. So now, how to actually, can I carry on from here? Use some of the new features to accelerate your current applications. If you don't want to use Renderscript yourself, and you've already written applications, or you don't want to use the NDK, then there's some great new features in Honeycomb in Android 3 and Android 4, Honeycomb and Ice Cream Sandwich. The first one was the fact that we've moved a lot of the UI now onto the GPU. Chet called it GPUI, GPU on the UI. And why now? Why? All of a sudden, we've got these dual-core processors, and soon that Tegra 3 with the 4 cores of the graphics, the 4 cores for the CPU, the 1 core for standby, and then the 12 cores on the GPU. It's like a 17-core monster. Why on earth would we need to move the UI onto the GPU at this point? Well, it's because the number of pixels have been increasing so quickly. If you look at this graph, how fast these devices can copy graphics from the frame buffers and from the memory onto the screen isn't keeping up with the number of pixels. So this is when it's not hardware accelerated. This is if you're using software rendering on a device, you're trying to get the graphics onto the screen, the memory copy speed would need to be double what it is now to be achieving decent frame rates. Moving it onto the GPU, of course, means that we get direct access to the frame buffers, direct access to the native windows, things like that, which means that the copies are almost instant, 0.001 of a millisecond at a time. Whereas in software rendering, we had a pipeline that looked like this. You draw the view, it draws the canvas, it gets rasterized and displayed. Now with the GPU, it goes to the Opengl renderer. Even for the UI of the devices on Honeycomb and Ice Cream Sandwich, it goes to the UI, the Opengl renderer first, through the GPU, and then down to the display. And that gives us two really, really good distinct advantages, even on top of that memory copying speed. If you look at the number of triangles that need to be drawn to draw a list, or a button, or a path, all these things can be accelerated now with hardware accelerated equals true. Or, with Android 4, if you target the SDK version 14, we already turned that hardware acceleration on for you now. And the hardware acceleration can be done at any level. It can happen at your entire activity, your entire application, a single activity, a single view, or even around a couple of lines of code. You do it in your application, you just say hardware accelerated equals true, or inside your activity. But inside code, you can set the flags on a single window, or you can set view, you can set the layer type. And this is one of the cool things, the layers on Android. Maybe you need to check if your surface is accelerated or acceleratable. Of course, as with all awesome systems that are high performance, there's going to be some caveats. And unfortunately, these mainly revolve around the canvas class at the moment. So if you're hoping to move to Honeycomb or Ice Cream Sandwich and find your canvases magically accelerated, in many cases they are. But in these cases, if you're using the clip path, clip region, draw, picture points, text, these things, then these particular parts of your canvas won't be accelerated. Many of these are due to not having similar equivalents in Opengl at this point. Again, there's some limitations. If you use these methods, you're not going to get 100% compatibility, but most of it will work. So, this new hardware-accelerated drawing model. In Android, you good Android developers out there, excuse me, this used to happen. If you invalidated a view of your view group, any single small part of your view group changes, it's going to call up. It's going to invalidate the group. It's then, in turn, going to invalidate the root, and then it's going to send the draw back down again. This can mean quite a lot of remeasuring, relaying out, and redrawing, which isn't ideal, and it's not your fault, it's just the way that the system worked before. In the new system, we have something called display lists, and they're pretty transparent to you. You don't even know that they're going on in the background, except for the fact that because the way we're doing drawings changed, you have to slightly think about it in a different model, so that when you see artifacts on screen, you'll know why they're there. So now when we draw a view group, we cache the list of methods that were called to draw that view group. So in this particular case, when we're drawing a button, instead of relaying out the entire button each time it gets redrawn, we store this display list, which says save, draw patch, clip rec, translate, draw text, and restore. And this display list is much, 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 much faster to run through this exact set of commands than remeasuring and relaying out the view as we did before. So the new model, you invalidate your view. We have these display lists here, which got cached when the first view was drawn. When that was drawn the first time and it was run through, we cached the set of display lists on the right-hand side. And now, if something changes on the left-hand side, we can just say the equivalent display list needs rebuilding. So if you invalidate view B, it could be a button. We say display list B is now dirty. We invalidate the view group, and that just says rebuild the display list. And most of it doesn't need to change at all. So we just rebuild the display list for part B and draw the group again. All the other parts of the view, how to draw those is already totally cached. How to lay them out, everything is all cached already. So in an example on the Zoom, on Honeycomb, if you touch the Wi-Fi settings up there, previously this entire view group would be invalidated, just because we put an alpha blend over the top. You would have to do this. You'd have to redraw the background, redraw the panel, redraw the selector, redraw the Wi-Fi, and run through all these things. And these draw commands from Android, there's the measuring, the laying out, the drawing. These are quite expensive. Now we just do this. You draw the selector on top and draw the display lists for everything else. We already know how to render everything else. What this means for you, because we're not relaying out the whole thing, is that if previously you expected the entire view group to get redrawn, so just by invalidating a small part of it, you expected the whole thing to get redrawn, that's no longer going to happen. You now have to invalidate each individual part of the view group, or if it's the entire view group, you can just invalidate that whole bar to ask for it to get redrawn again. So if you're running your application, if you turn hardware acceleration on, and you're noticing graphical glitches when you're doing these tick boxes and playing with view groups, it's more than likely it's going to be because of this, that the areas you assumed were being invalidated from a child being invalidated are no longer invalidated. So you're going to have to add an extra invalidate line in just to clean up that row. What? Huh. That was worrying. And now it's finished. No. So again, this also works for view groups. So before you would invalidate a view group, it would invalidate the parent and come back down and do the draw. Hello? Which would draw both views again. Now if you invalidate a view group, it marks the display list of the view group as dirty, invalidates, redraws, and rebuilds. So you can see that we already have the display lists of all the separate parts of the view. So every single thing that you want rebuilt and redrawn needs invalidating now. But it does make for a much, much, much faster rendering engine. So many of you, when you set to hardware acceleration, you'll notice improvements without any problems. And if you do have problems, have a look at the invalidation. The second part of this new model is layers. You can now set a layer type in Android. And there's, well, we'll see them in a minute, the different layer types. The benefit of a layer is, even with display lists, there's still rendering to do. If you render to a layer, and then you've got this off-screen image of everything that you've rendered. So we build up the display list, we build everything up, and then we draw it previously to a display, and now we draw it to a layer first and then to the display. We can do operations on that layer. First of all, if you just want to move it around the screen, that's great. You've got it rendered on the layer. But secondly, you can make changes to the entire layer at once without having to do any redraws. So let's have a look. First of all, we've got no layer. That's the current drawing model in Gingerbread. No layer at all. You're just drawing to the screen. Now we can have software layers. Software layers are very compatible, but they're rendering on your Dalvik heap space. And heap space can be expensive, can include a lot of garbage collection. Sometimes they garbage collect your slides. Hey, I don't know what's happening back there. And then you've got the hardware layers. Just by adding this one line into your view, view.renderType hardware layer, you're rendering your entire view directly onto the GPU memory. And you can imagine the kind of performance gains that has for you. For any single view you want to, you can just say View, Hardware Layer. And of course, this is now taking a lot of your graphics memory up. It can make it slightly harder to debug as before, but you get the OpenGL acceleration. You get that direct copying of memory from the graphics memory onto the screen. Things can go super, super fast once you set your layer type to hardware. Performance-wise. So we've talked about display lists. Previously, it could take 10 milliseconds to render out a list view, a scrolling list view on Android. It could take 10 milliseconds. Whilst we're using display lists, we have a 5 times increase in that, and it gets it down to 2 milliseconds. If you render that display list to a hardware layer, you can see it's 0.009 milliseconds to re-render that view onto the screen again. It's sat there, it's in the frame buffer, it's waiting to go. And you get the benefit of visual effects. So say you render the entire Honeycomb UI, all the icons, all the text, everything onto a hardware layer, but then you want to gray it out, reduce the contrast or the color balance of it. You can reduce that entire layer at once into black and white just by applying an operation to it. And it's done on the GPU instantly. You don't need to re-render anything. And here's the code for it. So you have your view, which is the page, that entire rendering of the Honeycomb UI. You set up a paint. Paints, you'll have used them on surface views, things like that before. They have many operations. Set a color filter on the paint to say that you want the saturation of the entire view to be 0. And then when you set the layer type to hardware, you apply that paint object to it at the same time. And it all renders to that hardware layer with 0 saturation. Supposedly easy. As I say, if you do have issues with that, you can go for the software layer. The software layer is still going to be faster than no layer at all, and it's going to be the most compatible. But if you want to do some funky animations, all these functions are supported on hardware layers. So you can do alpha blending, XY positions, translation, scaling, rotation, pivoting. You can render your view to a layer, and you can do all of these directly on the GPU using a hardware layer and those paint objects and the animations. And I recommend if you're going to do this, if you're going to translate a view across a screen, do something funky that you want serious, smooth, high frame rates for in Dalvik, set the hardware layer, do the animation, and then turn the hardware layer off again afterwards. There's no loss in setting it to a hardware layer and turning it off. But if you didn't turn it off again, you're going to be keeping a ton of graphics memory. So we have layer-friendly properties as well. Display lists and layers are now built to work together. So you get all the advantages of the display lists, that we're caching how it was built. But also, when you render that view, which is rendered with display lists, onto a layer, there's an extra performance gain for you. So for example, we have a display list set. Here, view B is a button or something. We want to rotate it by 45 degrees. And you've set this to be a hardware layer using display lists. Again, just a couple of lines of code. Now when you rotate view B, we can run through the invalidate, the mark dirty. And whereas before, this would be the display list for drawing button B, the system knows how to use these properties that I've listed on that previous slide, the alpha blending, the rotating, the skewing, things like that. So all we actually need to do is add the set rotation B into the display list. And we do this for you as well now. If you're on a hardware layer, we'll just redo the display list like this. We won't relay out, we won't redraw, remeasure. We'll just update the display list, because the display list and layers now work together to give you a high performance application. Again, this isn't something you need to directly worry about, but if you see issues in your Android application, it's great to know the model of how the new rendering engine's working, because with that, it's much, much, much easier to debug. So you set your layer type to hardware, you can do a rotation, and you end up using the display lists and the hardware layers to get this rotation of super fast graphics memory rendered objects onto the screen. And you haven't had to use the NDK, you haven't had to use Renderscript, any of these things, or even OpenGL. You just say hardware layer and rotate, and the new model means it's going to happen. Of course, what I said before about removing the hardware layer afterwards, you can just, on your animation, put an animation listener. So once the animation's finished, just set it back again to no layer type. Free up all the memory. It'll come back to you. So when hardware rendering, a couple of things to be careful of. If you're not using hardware layers, set alpha is really expensive. 2 times the fill rate. If you're on a hardware layer and your GPU supports alpha, you've got no problems at all. Reuse the objects. Again, common sense things, right? If you've loaded the bitmaps, don't change them, and don't change the paths too often. So yeah, that's a whole lot of information in about 35 minutes. A whole lot of information that covers Renderscript, NDK, Dalvik, Opengl, display lists, layers. But with a reasonable knowledge of these things, and maybe the deck of slides later on, you can make your Android applications smoother with minimal effort. Remember, at the very start, we said minimal effort. All these things, hopefully, go in to you having a better Android application. Thank you very much.